Hi everybody, in our previous video we calculated the F statistic for a one-way ANOVA, or analysis of variance. Now in this video we're going to figure out what that F statistic means, or what we can learn from it. As a quick recap of what we did, Nadine came up with some fertilizer that was supposed to increase the growth rate of these plants. And what she didn't know was which amount was best, which amount was most ideal for the plants. So she created 4 different groups and gave each group exactly identical treatment and exactly identical circumstances, except for she gave them different amounts of the fertilizer. So in one group, she gave them only water. There was no fertilizer whatsoever. That was our control group. In another group, she gave them only ½ an ounce in the amount of soil, mixed in with the amount of soil. In the third group, there was 1 full ounce of the fertilizer mixed in with the soil, and in the fourth group, 2 full ounces mixed in with the soil. Now what she wants to see is which group does the best, or are they all the same? That's what we're interested in. Now you'll recall that each group had 7 plants within them, and so there was a total of 28 plants that were planted, or seeds that were planted. And you'll recall that we calculated a final F value, an F statistic of 49.06. So now what we're going to do here is figure out, what does that mean? What can we learn from that statistic at this point? And it's important to recall the 2 options here, the 2 possibilities that we set up before we did any of this. Our default hypothesis was that the independent variable, the fertilizer, has no effect whatsoever on growth rate. And so they're going to be exactly the same. The control group's going to be the same time as the ½ ounce group, as the 1 ounce group, and as the 2 ounce group. Okay, and so that would look like this, is that the means didn't actually look any different. That's possibility 1. Another possibility is the alternative hypothesis. The alternative hypothesis would say, if we found a statistically significant F value, we can reject that null hypothesis and say there's something wrong with it. And actually, at least one of our means was different from at least one of our other means. In other words, some of the plants appear to have grown faster or slower than some of the other plants on average, depending on that group membership. And that would look like this. Our alternative hypothesis is simply there's something wrong with our null hypothesis. There was some statement in that null that was not correct. Now, which possibility it is, we actually need to figure out. So which of these hypotheses is correct depends on whether we have a statistically significant F value. So that's what we need to figure out now. However, of course, just like you've seen in our previous tests with independent samples t-tests and dependent t-tests, we need to know the degrees of freedom that this test has before we can decide what is our threshold for statistical significance. Now, it's a little more difficult with analysis of variance because we actually have 2 sources of variation that we need to take into account. The first source, I guess it doesn't matter the order, but one of those sources is the between groups variance. In other words, that's how many groups we have. So we'll take how many groups we have and then subtract 1 from that. You'll see that in a minute. Then the other source is how much variation we had within the groups just generally. And so that's based primarily on how many people there were present in our observations, if we're doing social science research. In Nadine's study, it's how many plants there were generally, although it's just a little bit more complicated than that. So luckily, these degrees of freedom are built into our F equation, so we actually already calculated them. We just need to go back and look at our math to figure these out. I'll show you the equations anyway, though. So let's take a look at that equation. This was the equation, right? This is the equation for an ANOVA. This is our control group stuff. This is our ½ ounce group stuff. This is our 1 ounce group and 2 ounce group, and so on. Now, the between groups variation, or the between groups degrees of freedom, I should say, is located right here as sort of the denominator of the numerator. Okay, so k minus 1 is the equation for our degrees of freedom for the between groups variance. K, of course, just means how many groups are there, and in this case we had 4 groups. 4 minus 1 is 3, so we had 3 degrees of freedom. I'm jumping ahead though. Our within groups degrees of freedom are of course located down here in the denominator of the denominator. It's this little guy, n minus 1 minus k minus 1. Now n minus 1 is the total degrees of freedom, but that's actually not really useful for us for anything beyond this. So we'll take our total degrees of freedom and we'll subtract, as you can see, our between degrees of freedom, and all of that leaves is our within groups degrees of freedom. And so that's the 2 things that we need. So as I said, for our math, we had a value of 3. This is our equation. I went back. This is sort of as we were almost done solving this equation. This is in the previous video. This is what we had, right? We had 4 groups minus 1, which of course equals 3 degrees of freedom for the between groups variance. And in our denominator of our denominator, n was 28. 28 minus 1 is 27. 27 minus 3 is, of course, 24. So we have 24 degrees of freedom for our within groups variance. You might see them symbolized as this df subtext between and df subtext within. In some textbooks, you'll see a df1 and df2. I just found that needlessly confusing, so I'm more explicit here in what I'm talking about. Okay, so now we have our degrees of freedom, and we do what we did in our previous tests also. We look up in an appendix, what is our critical value for a test with these characteristics? In my textbook, it's Appendix C. If you don't have my textbook, you can, of course, look up on ANOVA critical value table on the internet, and you'll find all sorts of tables. They're organized all slightly differently, but shouldn't be too difficult to figure out. So I'll show you mine. So here's what Appendix C looks like in my textbook. As you can see here, just like in the other appendices that we've used, these are the critical values, at least for the t-test. These are the critical values, meaning these are the minimum values of our statistic that are required to be statistically significant given these characteristics. In other words, as long as our test has these characteristics that we'll look up, this is the minimum value it needs to be statistically significant. So again, up here you've got the degrees of freedom for the between groups variance, and down here you've got the degrees of freedom for the within groups variance. Now, we had 3 degrees of freedom for our between groups variance. We just figured that out. So we're going to be looking down this column. We had 24 degrees of freedom for our within groups variance, and as you can see, 24 doesn't appear on this page, so we're going to have to skip to the next page. Now, I'll show you that section here in a minute. So it'll look like this if I zoom in, right? I've got 3 degrees of freedom for the between groups variance and 24 degrees of freedom for the within groups variance. So I find this corresponding row. Now, as you can see, there are 2 different rows within that row. The top row means that this is at a 5% level of significance. In other words, it's saying this value allows a 5% chance of committing a type 1 error if you reject the null hypothesis. In other words, it's if you say there is an effect using these critical values, you're allowing a 5% chance of making a mistake. Down here, you're allowing a 1% chance of making a mistake. Okay, so this is better, of course, but this is perfectly fine and acceptable in conventional statistics. So we'll take a look here. So what is our value? Obviously, if we have 3 degrees of freedom here and 24 degrees of freedom for over here, and we'll start with the 0.05 level of significance. Of course, we end up with a critical value of 3.01. A critical value of 3.01 means that that is the lowest possible F value that would be considered statistically significant at 0.05. In other words, a F value of 3.01 would be expected only 5% or less of the time if there's no effect of your independent variable on your dependent variable. Therefore, we can go ahead and say that we have a meaningful difference if we have an F value we calculated of at least 3.01. Okay. So we calculated an F value in our last video of 49.06. 49.06 is, of course, much bigger than 3.01, and so we can say that our F value is statistically significant. In fact, at this point, we can now reject our null hypothesis and say it's clear that our means were not the same, and actually at least one of the means was different, meaningfully different from at least one other mean. Now, in fact, you may have also noticed that 49.06 is not only bigger than 3.01, but it's bigger than the critical value of the 0.01 level. Let's take a look at that really quickly. So if we go back in to our appendix, now if we use the p equals 0.01 criterion, in other words, down here, meaning we want an even lower chance of committing a mistake, then that's fine. We can use this criterion. And as you can see, that would correspond to a critical value of 4.72. And of course, our F value of 49.06 was much larger than 4.72. So we have a statistically significant F value that is also significant at the 0.01 level. In other words, it's less than 1% likely that we're making a mistake by by rejecting the null hypothesis. Okay, so here's what we just did, wrapped up in a nice little bow. We had a one-way ANOVA. We were testing the effects of fertilizer in different amounts on the growth rate of a plant. And we found that the group membership, in other words, how much fertilizer these plants got, actually did have an impact on how quickly they grew. We have no reason to believe that that was not true, and we have sufficient evidence to go ahead and reject our null hypothesis. And this is how APA, or the American Psychological Association, summarizes a statistic about an F value, at least what we have so far. This is our F, the F statistic. This is the degrees of freedom for the between groups variance. This is for the within groups variance. That is always the order you see it in if it's ever summarized, with between and then within. And then that's the actual value of the F that we obtained. And our p-value at this point, our statistical significance, is less than 1%. In other words, our probability of committing a type 1 error is less than 1% by rejecting the null hypothesis. Okay, now some things we don't know, however, are important. At this point, all we've done is the omnibus portion of the ANOVA. In other words, all we've done is decide which of our hypotheses is true, the null or the alternative. And our evidence so far supports the alternative hypothesis. So we now know that it's safe to reject the null hypothesis, but we don't know which group grew faster than which other group. For that, we have to do something called a post hoc test. So we will do that in the next video, and we'll see how all of that works. I will see you then.